compute the indefinite integral, the square root of 4 minus 36x squared over x squared with respect to x using a trig substitution. Now, when I first approach an integral like this, I want to remove as many of these numbers as I can. So I'll push them into another number r, and then I can work with my integral in an uncluttered way. So when we're doing these trig substitutions, there's two ways you can pull the numbers out. When you're first learning how to do these, you want to focus on getting a 1 in this first spot here. So the idea is, when I see this 1 here, it's going to be clear what I substitute into this part. Okay, you would want, say, a cosine squared, tangent squared, or secant squared. Now, when you get comfortable with how this works, it's actually better to go with a square root of r squared minus x squared. So we're going to use the second one here for the problem I have at hand. Now, what can I do with this term here? Well, I want to get x squared by itself. So I'm going to factor out a 36, but when it goes through the square root to the outside, just going to be factoring a 6 out. So we're really looking at the indefinite integral of the square root of 1/9 minus x squared over x squared with respect to x, and I'm going to let my r be equal to 1/3. So now we're going to work with the general integral, indefinite integral, square root of r squared minus x squared over x squared with respect to x. Now, the philosophy here, I want to put something squared on the inside of our square root sign, so that way that thing just collapses. Now, looking at what we have, if I let x be equal to r cosine of u, then we have square root of r squared minus r squared cosine squared of u. I could factor out an r squared. I have 1 minus cosine squared of u. That's going to turn into r squared sine squared. And then with the square root, it becomes r sine of u. So that gets rid of our square root. Now we just have to check the rest of the integrand to see what we're left with. Now, for this equation, I'm going to take derivative of both sides. Remember, r is just a number that we're using as a placeholder. So we'll have that dx equals minus r sine of u du. Okay, so the derivative of cosine is just minus sine. Now, I substitute. So our square root term is just going to be r sine of u. dx is minus r sine of u du. X squared is going to be r squared cosine squared of u. So we put all this together. The r squareds go away, and I'm left with sine squared over cosine squared, which is just tangent squared. Now, how do we take the indefinite integral of tan squared of u with respect to u? We switch over to secant squared. Now, to do that, I start with cosine squared plus sine squared equals 1. We divide through by cosine squared. That gives me 1 plus tan squared is equal to secant squared. And then I push the 1 to the other side. Now, when we substitute, we're going to have a minus 1 in front. So that gives me the indefinite integral of 1 minus secant squared u du. We integrate term by term. The 1 goes to a u. Secant squared u goes to tan of u. And we put in our constant of integration. So this is our answer in terms of u. Now, we want to put our final answer in terms of x. So we go to the equation x equals r cosine of u. I want to isolate the u here, so I can push the r to the other side. Then we want to remove the cosine. So to do that, we have to recall how inverse functions work. If f and f inverse are inverse functions to one another, then f composed with f inverse of u is equal to f inverse composed with f of u is equal to u. So they'll cancel each other out when we compose. If I apply inverse cosine to both sides, then the cosine will cancel, leaving us with u equal to inverse cosine of x over r. And now I can substitute this into here. We have this now. So we could stop there, but it's possible to simplify this middle term. And we'll want to do that for when we check our answer by taking the derivative. So I want to find tangent of u. We could do that by using a right triangle. So recall, if cosine of u is equal to x over r, I can set up a right triangle where the length of the hypotenuse is r, the length of the close leg is x. So we have x over r equals adjacent over hypotenuse. Now we can fill in the length of the opposite leg using the Pythagorean theorem. So we have square root of r squared minus x squared. I can find the sine, which is the opposite over the hypotenuse, and we can find the tangent, which is the opposite over the adjacent. So the tangent's what we're interested in. That's going to be square root of r squared minus x squared over x. We substitute this into here, and that's going to give us our final answer in terms of x, and we can work with this. Of course, we check our work. So we'll take the derivative of our answer, verify that we get back the function in the integrand. Now, for that, we need the derivative of inverse cosine. So recall, the derivative of inverse cosine at u is equal to minus 1 over the square root of 1 minus u squared. We take the derivative of inverse cosine of x over r. I use the chain rule, and I'll put a box around the x over r. So I want the derivative of inverse cosine of box, which is given by minus 1 over the square root of 1 minus box squared. Put x over r in the box, and then we multiply by the derivative of box by the chain rule. So that's going to be 1 over r. Now, we can push r into the square root as r squared, giving me minus 1 over square root of r squared minus x squared. For the second term, we take the derivative using the quotient rule. So you just work that out to get to here. And then I have to deal with these two terms with the exponents as 1/2 and minus 1/2. To fix this, we multiply by the square root of r squared minus x squared over itself. Now, when we multiply into each term, we're just going to add the exponents. So in the first term, we get a 0, leaving us with just minus x squared. In the second term, we get an exponent 1, leaving us r squared minus x squared. So we get to here, and this simplifies to r squared over x squared times the square root of r squared minus x squared. So we add our derivatives. To put things over a common denominator, I multiply the first derivative by x squared over itself. When we simplify, we get square root of r squared minus x squared over x squared, which is the function in the integrand. So our work checks out. Now, let's return to the original problem. So we have indefinite integral, square root of 4 minus 36x squared over x squared with respect to x. We factor out a 36, which comes out as a 6. We see that if I want to apply the formula, we have r equal to 1/3. So we have inverse cosine of x over 1/3, which becomes 3x, then minus square root of 1/9 minus x squared over x. Now, if we want to get our final answer to look like the original integral, I'm going to push this 6 to the inside as a 36. Then we get our final answer. Let's recall how we get the derivative of inverse cosine. We're going to use inverse functions and the chain rule. So first recall, if f and f inverse are inverse to one another, then we have that f composed with f inverse evaluated at u is equal to u. I'm going to let f be equal to cosine. Now, since these are equal, if we take the derivative of each side with respect to u, they stay equal. And we're going to need the chain rule to work out this side. So what do? We're going to cover up the inside or put it in a box. I take the derivative of cosine, which is minus sine of box, and then I put the cosine inverse of u back in the box. By the chain rule, we multiply by the derivative of the inside, which we don't know, it's what we're looking for. So it's just going to be the derivative of inverse cosine of u. On the other side, we take the derivative of u with respect to u, and we just get a 1. Now, that lets us isolate the derivative of inverse cosine of u. So we just push this to the other side. Now, we want to simplify this. So I'm going to have to give inverse cosine of u a name. I'm going to call it t. And just recall the inverse cosine is returning an angle. Now, how do I unravel this? Well, I can apply cosine to both sides, and then cosine and cosine inverse cancel out. So I have the cosine of t is equal to u. U, I could think of as u over 1, and then we can apply that to our right triangle, where the adjacent side to our angle t is u, and the length of the hypotenuse is 1. So that means the length of the opposite side is going to be square root of 1 minus u squared. And then the sine of t is going to be equal to opposite over hypotenuse, which is square root of 1 minus u squared over 1. Now, we just take sine of t, replace it in our formula, and that gives us the derivative of inverse cosine.